Welcome to the session on concurrency without pain in pure Java. My name is Venkat Subramaniam. Let me talk a little bit about what we're going to do here today, and then we'll get into the main content. Quickly, we'll talk a little bit about what's the reason for excitement on concurrency. I'll talk about three specific models here for concurrency, and we'll use quite a few code examples. I'll be writing some examples, demoing it. Best time to ask a question or make a comment is when you have it, so please don't wait till the very end. Just about any time is a great time for questions, comments along the way. So let's get started. Why all of a sudden interest in concurrency? Well, let's give credit where it's due. We've had multi-threaded programming in Java from day one. If you recollect, when before the time of Java, those of you who had to program in languages like C++, we had to pick really different libraries along the way, and when you program for a different platform, you had to learn a different library and use a different library. One thing that Java did really well was to give us this one common API. We could start the thread and be happy with it. But then still, why are we still excited about concurrency? It's the old problem, isn't it? Well, it turned out that in about 2003 timeframe, things kind of started changing. That was the day when this guy went to his boss and said, it ran really fast before it melted. And he was talking about the chips, of course, right? And we went along the lines of multi-core processors. Now, with multi-core processors, multiple threads are on steroids. On a single processor, multi-threading is more like multitasking. But when you have multiple cores, it's really on steroids. But how does it really matter? Again, we've had concurrency library from day one. What's the big difference? Well, let's take a look at an example. Imagine for a minute that everybody in this room is a thread, right? And imagine we're all, running in processors. And I'm going to use some people in the front row. These are victims for me here. As an example, what's your name, sir? Chuck. So Chuck is our first thread, and he wants a piece of data. What is he going to do? Chuck walks up to the wall, which is the main memory, gets the data, copies it down on his notepad, comes down and sits back here and starts working with it. Let's say a few minutes goes by, and what's your name, sir?
James.
James wants the same data, right? And he's going to get up, and Chuck looks like a nice guy, being a nice guy as he is. He says, James, let's share the data. And they have, space here. They put it on the desk here, and then they start sharing the data. Well, you see, this model is already broken, isn't it? James and Chuck, did you really plan ahead to sit next to each other? Purely coincidental, right? Yeah, they confirmed that. So the point really is that they're just coincidentally sitting next to each other, and they start sharing the data, right? Now imagine this is a one-core processor. Things kind of already broken, but they pretend to work correctly. But let's say a little bit later, we have multiple cores in the system. And let's say somebody over there, like he's getting up right there to get some data, as you can see, pretty nice demo. And he wants the data. What does he do, right? Well, he's obviously going to go all the way to the main memory to get the data. He's not going to take a peek at what these guys are working on here, right? And the point really is that on a multi-core processor, not only do we have multiple caches, we may end up having multiple levels of caches. So in other words, on a single processor, we normally have a cache, and the data kind of is in the cache, and the operating system kind of moves things around. But in a multi-core processor, there's multiple levels of cache and multiple locations of cache. And as a result, the chance of an application being broken is much more. I got an email from a guy, and I thought this was funny, but I don't think he thought it was funny. His email said, we have an application in production for the past 5 years, and it's working fine. And his email goes on to say, last week my company bought us a multi-core processor, we deployed the application on it, and all hell broke loose. His email goes on to say, don't tell me to do the right thing. I know what it is, I cannot do it. So tell me what's the quick fix. How can I make this application work on this multi-core processor? And I emailed back to him saying, it's very simple. Walk up to the multi-core processor and turn off all the other cores. Right? And the point really is you cannot quick fix these problems. Now, why is this such a big problem? The reason is most Java programmers, including me, have not really taken the time to understand something extremely important. And that's called the Java memory model. The Java memory model talks about how the data goes from the main memory to the working memory, where the working memory is a combination of registers and caches this object is going to use. And without understanding the Java memory model, it's incredibly hard to get this right. If you're not sure about this, I recommend highly a fantastic book. It's a book by Brian Gates called Java Concurrency in Practice. If you haven't read that book, that's one of the most scariest books for programmers. And when you read that book, you realize how important Java memory model is. And as you're reading the book, you will realize it's impossible to get concurrency done correctly without understanding that. But then once you finish the book, you realize it's impossible to get concurrency even if you understand the Java memory model. That's how sad this is. Let's talk about why this is such a big concern. Now let's take a look at an example of this and see what the current state of concurrency is. So I'm going to start with a little example here. Now, let's say for a minute that we have an account class. Very simple example to start with, right? A simple account class. And I have a balance in the account, as you would expect. I've got a constructor which takes the initial balance value, no surprise there. And of course, I have a deposit method. And within the deposit method, I'm going to increase the balance. As you can see there, I'm adding to the balance. Not a big deal, right? I have the withdraw method. I want to make sure there is enough money first before I withdraw. So right there, I go ahead and withdraw the money. And you can see that I've withdrawn the money based on the balance amount. And of course, finally, the most obligatory get balance method is also available to us. So as you can see, that is our account class, just a little POJO, nothing really complex at all, right? So a deposit method, a withdraw method, a get balance method, that's it. Now let's take a look at the code that's going to use this over here. And what I have here, as you can see, is a little account I've created, 2 accounts I've created. And each of them have a balance of $1,000 in it. I want to transfer money between those two, and I want to transfer $500 between those two. And of course, once I transfer money, I want to display what the balance is. Of course, this is using a transfer method within a so-called account service. Let's look at the account transfer method itself. Oh, I don't have it. Let's go ahead and write it. So public static void, and I'm going to say transfer. Where do I transfer from? Well, I'm going to say final, and this is going to be an account from, and I want to transfer this to some account, so we'll call it final account to. And of course, we got to tell him what to transfer, and that's the amount I want to transfer. So right there is the transfer method. Of course, we have to implement the transfer method, isn't it? How do I implement the transfer method? Well, let's give this a try. How about saying to.deposit, and I want to use the deposit method that we already have, and then I'm going to say from.withdraw, and I'm going to specify the amount I want to withdraw. Now, I know what you're thinking. You're thinking, God, let this guy not work for a bank, right? Because we just gave the money to this account, turned around to the other account and said, can I have the money, please? And he says, what money? It's too late. Close the door. Bring back the guy who we gave the money to, right? Well, yeah, that kind of looks a little scary. But maybe we want to fix that a little bit. So let's say if the from.withdraw was successful, then maybe to.deposit amount, maybe that's a little bit better and safer as well. All right, so that's all great, but really the concern is we want to create multiple threads and access this account repeatedly. So obviously this account is not thread safe at all. So what do you think I should do to make this account thread safe? Any ideas? I can hear the few whispers. Be loud. Synchronize, you said. So I'm going to put synchronized over here, right? Synchronized. And I have to put synchronized in the withdraw method as well. But I'm kind of thinking, do I need a synchronize in the get balance or not? Anybody else thinking no? Yeah, a few people thinking no. So we can, I love democracy. We can vote on this, right? And then we can see who made things work. Well, of course, there's a problem here, right? Because it's got to be one or the other. Well, if you don't put synchronize, what happens? Well, it turns out, if you ask most Java programmers what synchronize does, they'll tell you it gets you a lock. Unfortunately, that's not totally true. That's only partly true. What synchronize does is it helps the code cross the memory barrier. It helps the program cross the memory barrier. So every time you call a synchronize method, not once but twice, we cross the memory barrier. Similarly, when we access a volatile variable, when we call thread.start, thread.join, when we call wait on objects and notify on objects, there are quite a number of methods when we cross the memory barrier. Now, crossing the memory barrier is extremely important, but not crossing it when we have to cross is as bad as crossing it when we shouldn't. Because if we cross memory barrier when we shouldn't, we end up exposing invariance incorrectly, and that could become a problem in semantics as well. So this, as it turns out to be very, very difficult to solve. Okay, I put synchronize on this. What do you think? Are we done? Not really, because I have to worry about synchronization in here as well, isn't it? So I'm going to say synchronized over here, and then this is going to be on the from account, and then I'm going to say synchronized on the to account as well. And then, of course, within the synchronized block, I want to perform this operation. Now the code is thread safe and we are done. What do you think? I hear see a few people laugh already. What do you think? Can we have the confidence we are done? No, of course not. In fact, I got the best answer in one of the talks I gave a few months ago. This guy was swift raising the hand and said, of course not. I said, how? He said, it's been only 5 minutes since you started, cannot be done. Okay, absolutely, that's one way to look at it, right? So absolutely, so what's wrong with this? I heard deadlock. Gosh, there's not only deadlock, there's also a live lock. What happens when you call synchronize? We request for a lock. Well, what if no lock is available? What happens? You wait. How long do you wait? Forever. How does that sound to you? It's pretty stupid, isn't it? Would you do that at work? You go to the coffee machine to get a coffee, there's no coffee? Right? So what are you doing to it? Waiting for coffee to fill up. And how would exactly that happen? Right? So absolutely that's kind of ridiculous, right? So we don't want to call synchronized, but how do you really put a timeout on synchronized? That's the right answer. There's no way to do that. Okay, that's one problem, a live lock. But there's also a deadlock. How is there a deadlock? Because two threads come in at the same time, at the fateful moment, they both end up transferring money across the two accounts in the opposite direction, right? Here's a way to think about deadlocks. There's a boy and a girl in the house. In the morning, the boy and the girl run to the kitchen. The boy grabs milk, the girl grabs the sugar, and they both wait on having breakfast because one has the sugar, the other has the milk. What do you have on hand? Not a deadlock, a parental nightmare, right? So obviously we have a way to resolve this. And how do you resolve this? You say, kids from tomorrow, you have to get sugar before you can get milk. In other words, you can put ordering into the picture, right? So one way to remove this deadlock problem may be to say, somehow in the account we'll put an ordering, and we could say account, and we could say accounts equals, and we could say, for example, arrays dot sort, and we could sort the accounts from and the to, in this case. And once we sort the from and the to, don't worry about the syntax at the moment for me. And then once we sort the accounts, probably what I should do really is create the account structure here, new account like that. Now once we create the from and the to accounts, what we could do is arrays.sort, and then we can put the accounts to sort. Then we could say over here, accounts 0, and then this could be accounts 1 to really lock them in that particular order. Well, even if that removes the deadlock, we still have the live lock, and we have to start putting lock interface and do a lock and try lock and release the lock. That would involve putting a try and finally block. What do you think that's going? And once you finish all of that, is the code thread safe? You're not sure anymore, right? And while they're struggling with it, the boss comes over and says, how's it going? What do you tell the boss? Yeah, I have no clue what's happening, thanks for hiring me, right? You can see how this has become complex, isn't it? The other day, I wrote a piece of code, and I had called synchronized on it. On the way to home, I was thinking about the code. Now I know not to do that. Thinking about code as I go home, right? And I thought to myself, did I synchronize at the right level? As soon as I go home, I check it, look at the code, and sure enough, I have synchronized in the code, but it was in the wrong place. And once I figured out what was going on, I fixed the code, and now I'm sitting there wondering, where else the code is broken? I don't even know that. How do you feel about that? Pretty scary, isn't it? Because we are trying to solve concurrency problem, and we are not sure anymore if the problem is solved or not. We're not sure if we locked it at the right place or not. So in a sense, we really are at a loss when we try to do synchronize. In fact, I love this so much, I have a special name for it. I call it the synchronize and suffer model. And the reason why this is a synchronize and suffer model is, the minute we get into synchronization, it is extremely hard to reason through the code and ensure that the code is correct from the point of view of locking. So let's summarize what we talked about. When you forget to lock or you lock at the wrong place, the Java compiler gives you an error, correct? No. Okay, well, let's try this again. When you lock at the wrong place, the Java runtime gives you a warning. No, I hear people laugh. No, it doesn't. Well, what does it do then? You don't have a clue, right? It's unpredictable. If you're lucky, it fails on your machine. If you're not so lucky, it fails when you do an important demo, right? So this is what I understood. Programming concurrency on the JDK is like working with a mother-in-law. She's just waiting for you to fail. And we cannot have that kind of friendliness to develop enterprise applications. Now, don't get me wrong, I love JDK. It's awesome. It's very good. It's just that it's way too low level of abstraction for us to be writing concurrent applications in. In a way, I would like to see the JDK concurrency library as the assembly language of concurrent programming. In fact, that's true today because most of the solutions that I'm going to talk about today use the JDK concurrency libraries like fork join and other things, but they use it so we don't have to. So we can build on a higher level of abstraction and get focused on our problem we are trying to solve. So I want to talk about two problems we're going to look at today, two ways to solve the problem today. One is the so-called software transactional memory, and the other is called the actor-based concurrency model. So let's talk about what these two approaches are. Well, these two approaches are fundamentally different in the way they approach the problem. It's kind of interesting how they really approach this. Now, what is the real problem really? The problem really is that we are dealing with shared mutability, isn't it? So if you really think about it, is mutability such a bad thing? Well, guess what? We've been programming in Java for a good 15 years, and mutability is the way of life in Java. We are used to it. So mutability cannot be really that evil, right? What about sharing? Well, sharing is a good thing. Remember what mom told us, right? Sharing is a good thing. So mutability is all right. Sharing is great. Shared mutability is devil's work. And the minute we bring in shared mutability, we got all these problems we have to deal with. So there are two different ways to approach it. Well, the functional programming guys are telling us that everything will be immutable. We will change nothing. And you sit there and wonder, what are you guys smoking? How could you develop an application where nothing changes, right? Well, the point really is in a functional programming style, you don't change anything in most of the application, but you have selected areas where change happens in a very controlled fashion. And of course, they are very clever. They call it monad, so nobody would understand what they're doing. But the point really is that we kind of control those structures really well. But when we program in Java, it seems out of reach to even think that we can program in functional language. What do we do as Java programmers most of the time when we write code? So there are two approaches we can think of. One is this fundamental different shift in the way we handle shared mutability is software transaction memory, which is bring it on, I'm going to handle it for you. I'll go into the details of that in a few minutes. And the other approach is where we can deal with mutability, but what I would like to call as an isolated mutability, where we isolate mutable variable so no two threads can ever get to it at any given time. We'll talk about that also a little bit along the way. But one of the beautiful things about the shared mutability, the software transactional memory is that we have a separation of state from identity. What does that mean? Well, if you ask me, what's the stock price at 1 o'clock today, you would say that's some crazy value. And 1:10, what happens? 1:10, what happens? That value changes. Well, that's one way to look at it. But a different way to look at this is a stock price never ever changes. In fact, that's really true. Because every stock price at a given time is historic, never to be modified into the future. So you can go back in time and say, what was the stock price of a particular company at a given time on a given day, and that value never ever changes. So what you do is you say, the values of the stock are all completely immutable, and they never change once they are created. And I have an identity referring to what these stock prices are at a given time, the current price. The identity changes, but we'll get back to that in just a minute. But the stock price itself, the state itself never changes. Now think about this for a minute. James wants access to the stock price right now at this instance, so I'm going to give him the stock price. And exactly at the same moment, Chuck wants access to the stock price also. And I want to give this price to Chuck as well. But how many locks should I hold on this object when I give it to these two people? None at all. That's correct. Absolutely right, because this is totally immutable, right? It cannot change. No need to hold a lock. Great. That's fine for the state. What about the identity? Well, the identity in software transactional memory, STM, it's a managed to mutable identity. It's a mutable identity, but it's a managed to mutable identity, meaning it is controlled by an environment. It's a managed object. So here is the identity, and at any given time, I may say, here is the current value, here is the new value, flip the switch to the new value, and I can switch it to the new value at any given time. But on the other hand, you say, well, that's great, but how do you protect it? And the way STM deals with it is that managed immutable identity can only be modified within a transaction. Now you say, what is a transaction? Well, a transaction is where your code runs in what I would like to call as a cone of silence. So whatever happens in the cone of silence, nobody knows about it until you reach the end of the transaction, and either you commit and others can see the change you made, or you roll back and as if nothing happened, it just evaporates. So the point really is that transactions run in a cone of silence. Now, STM has been around for a while, by the way, but this was introduced into the JVM by Clojure. When Rich Hickey created Clojure, he implemented that into the language. Let's take a look at an example here real quick. I'm going to say for a minute, I'm going to create a balance over here, and I want to know what the balance value is. I'm going to define balance. Is going to be a 0 value. As you can see, the value is 0 right now, and you tell me, Venkat, go ahead and change the balance value to 100,000 now. I have to say I don't have a clue how to do that. And the reason is, it's a state and it's immutable in Clojure. You cannot modify states. You say, what do I do then? Well, we can modify references on the other hand. So what I'm going to do is, rather than keeping balance as a state, I'm going to change it to a reference over here. And you can see that I'm able to change the reference. Well, I'm able to access the reference. But I want to know what's within this reference. How do I know that? And I'm going to say in this case, give me the balance value. And notice it tells me the balance value is 0. Now I want to modify the reference. How do I do that? Well, I'm going to go ahead and say ref set. Balance is going to be 100,000. I'm going to change it. But notice one thing that's conspicuously absent here. I haven't mentioned anything about transactions to this code. So when I run this little program, you can see it blows up. And it blows up saying, illegal state exception, no transaction running. In fact, I get really upset. It screams loud saying, he touched me, right? And it's really unhappy this happened because you did not enter into a transaction. So in other words, imagine the beauty of this. States are immutable, identities are mutable, but only in a managed fashion. It has to run within a transaction for us to modify it. So what I'm going to do here is to say, all right, let's go ahead and create a do sync over here. And do sync is a way to enter into a transaction. And now that I've entered into a transaction, I'm going to go ahead and modify this. Notice this time he's not screaming loud. And now I want to go ahead and print the value of the balance at the end of this. And you can see quietly it was modified to a 10,000 at the very end. So in other words, you cannot modify a managed immutable identity unless you have entered into a transaction. Now you say, okay, that's cool. I see that you cannot, accidentally modify this. This is as if Java really evolved to say, if you don't synchronize the object at the proper place, we will scream loudly, right? Well, you see, the problem I have in the JDK concurrency is not that we have to synchronize. That's not my problem. My problem is it doesn't tell us if we don't synchronize. It doesn't tell us you are wrong. Instead, it calls the other JVMs and reports that we have a victim, another victim today, right? So we want predictability in the code. That's what is missing. Now notice how it's predictable here. It tells us, oh no, you cannot do this, and it fails loudly. All right, that's great. We can have transactions, but how does this really help? When multiple transactions are running concurrently, if the transactions don't collide with each other, meaning they're not trying to modify the same object at the same time, they all complete and go away, no problem whatsoever, and we never held an explicit lock on the object. On the other hand, if two transactions are trying to modify exactly the same object, what's going to happen? Imagine for a minute that I have something over here and Chuck and James both are approaching that and they want to modify that exactly at the same time. One of them will get to that first, make a change and commit it back to the memory, and the STM will go to the other transaction and say, I'm really sorry, while you were running, there was another thread under the covers that was working as well, and that took a precedence, and it automatically retries the transaction. We don't have to write a single line of code. The transaction is repeated automatically. Now, what if another time it runs and it turns into a problem, it will retry one more time. How many times will it retry? Well, in the case of STM and Clojure, it retries up to a maximum of 100,000 times. I had a guy very curious the other day. He said immediately, what happens after 100,000 times? That's called bad karma, right? Give up and go home, no point in retrying after that. The point really is that you don't want to have that much of contention anyways in your system. Concurrency is not a suitable solution in that case. So the beauty is, of course, you can configure that also in other systems. So you say, all right, that all sounds great, but we did check the title of the star, and you did say concurrency without pain in pure Java. Well, we're kind of willing to believe a little bit about this no pain part, but where's the pure Java part? All right, that doesn't look like Java, so we'll kind of move away from that. Now, it turns out that you don't have to program in Clojure to use STM. And it turns out STM in Clojure was implemented, take a while to guess, in which language? Java. So it turns out we can actually use this from Java. So that's exactly what I'm going to do. We are in Java right here. And I'm going to go to the account class right there. And let's remove all the synchronized mess we created, because that's not helping us after all. So I'm going to remove all the synchronized parts. As that doesn't help us also, the deadlock is looming overhead as we speak. So rather than doing any of that, what I'm going to do instead is I'm going to simply tell him that I want to use a managed mutable identity. How am I going to do that? Let's go back here and say import clojure.lang.star. Now, you say, wait a minute, you're bringing in a library here for me to use. How many of you use Hibernate? Of course. How many of you use Spring? Of course. You already have 100 jars in your class path. What difference does it make to put one more in the class path, right? So absolutely. So all that we're doing is putting clojure.jar in the class path. You're not programming in Clojure at this point. You're just reaching into that library at this point, isn't it? So I'm going to change this to a ref object. Now the ref here is the managed mutable identity. And in order to use that, I have to say here that I want to say this is going to be a new ref object. And I'm going to say this is going to be simply an initial balance I want to bring in. And similarly, I'm going to say get balance over here. And I'm going to get the balance plus the amount that I want to add. And I want to put this into the balance. We used a ref set on the other hand. We'll come back to that in a minute. So I'm going to say balance.set and set the balance. Notice I'm working with this object. Keep in mind that the ref is the managed mutable identity. And what is it going to hold? A reference to an immutable object. And we already know that in Java, the big I integer is immutable, right? We cannot modify that. Similarly, in the withdraw method, I'm going to get the balance right there. And if the balance is good enough, I'm going to set the balance this time. And I'm going to say in here that the balance minus the amount itself, and I'm going to set the amount. And finally, here is the getBalance method. And in the getBalance method, I'm going to say this is going to be integer object. And I'm going to just cast it to the integer and return that value to the caller as well. So what am I missing here clearly, though? That's right, transaction. I didn't create any transaction. Let's see what happens if I don't bring in the transaction. Back in the account service, let's take a bold step. Why don't we simply say, go ahead and do the to deposit first of all. After all, we can trust everybody in this world, right? So let's go ahead and say to deposit. And then, of course, I'm going to say from.withdraw and then the amount. Let's be very bold and see what happens when we do these steps. So I'm going to go back here and transfer that money through this account, assuming I wrote all of this correctly. Oh, it's complaining in this case. It says inconvertible type in this case. He's not happy with it. So let me go back and tell him what we are dealing with. Dref, I got to get the value out of him, right? So dref is getting the value out of him. Oh, he's complaining about exceptions. Of course, I forgot we're programming in Java, right? But as experienced Java programmers, we know exactly how to solve that problem. Okay, so we can move on. Oh, it's complaining about illegal state exception. Did you notice that? So we are back in the Java side, and it says, how dare you modify that reference? No transaction running illegal state exception. And there was a slap on my wrist for touching that object right now, right? Because I haven't entered a transaction. Making sense so far? So we have to enter a transaction before we can modify this. How do we enter a transaction? On the Clojure side, we use this wonderful thing called doSync. We're not going to use doSync obviously here in Java, but fortunately that method is available to us on the Java side using a class called the locking transaction. So what are we going to do here? I go to the account class first of all, and here I want to run this within a transaction. So I say locking transaction. So locking transaction, and the run in transaction. And I'm going to simply say here is new callable, a void of that. And I'm going to implement this method, public void call method. And within this method, I'm going to do that one operation. That's the do sync you saw innocently on the Clojure side, blowing up here on the Java side. But I got some good news for you. This code is simply sending a Clojure to a Lambda expression to the running transaction method. When Java 8 is available to us, that will look very concise and beautiful, isn't it? So there's hope for us in that regard. So what am I going to do here? I'm going to import over here java.util.concurrent .star because I want to bring the callable interface. And I'm running this within the transaction. So notice how I wrapped this call to run within a transaction. What is it going to do? What it's going to do is, when I come into the deposit method, it starts the transaction, and that one line of code is running in its own transaction at this point. And then when we are done with it, in the withdraw method, I need to do something similar, but I'm going to change it a little bit. And rather than a Boolean, I'm going to make it a void method. And then I'm going to run this whole thing within a transaction. So I created a transaction right there. And then within that transaction, I'm going to go grab this code and drop it in there. And I'm going to say, if there was enough money, go ahead and do the transaction. If there was not enough money, by the way, then I would like to simply say, throw new. And I'm going to say, throw new. What am I saying here? Runtime exception. And this is going to say, this exception says not enough money, right? Of course, if there's no enough money, we cannot be giving this money away, right? So we are throwing an exception at this point. Am I making sense so far? And once we do this, hey, what about the transaction for the get balance? Well, thankfully, dref runs in its own transaction, so we don't have to waste our time creating that here. But if we are running in another transaction, it will just run within that, no problem at all in this case. Great, so far so good. But I got to go to this guy here and do the same thing here as well. So I'm going to grab the two imports we need from up here. I'm going to put this into a transaction. But before I do that, I want to report a failure as well. So if there was an exception, I want to report there was an exception. So I'll just output here exception.getMessage to say something went wrong. And of course, in this code, I want to run this within a transaction. So I have the transaction boundaries created. And within that, I'm going to say deposit and withdraw money, and we call that method. Let's go ahead and see if this is working so far. We're transferring $500 between the two accounts. Let's make sure we've handled the exceptions properly first of all. So this guy is going to throw an exception potentially. We catch it right here. In the account class, we have done the throws exception up here for this guy. Potentially this could throw exception as well. We'll put that in there. And then of course this could potentially throw an exception. We'll put that in there. So that seems to be all right so far. Assuming I've not messed this up totally, we can run this and see what happens. Oh, line number 15, return statement is missing. Let's go fix it. So line number 15 over here, what did I do? I have started a transaction over here, and I'm going to run this whole thing within a transaction, but I haven't finished this transaction that I started up here, isn't it? So let's go fix that real quick here. I'll just go ahead and remove that, and it's easier to just get that back in Squire here. So I'm going to say run this one call within that transaction for me. All right, there we go. So let's go ahead and run that and see what happens. Oh, deposit must be declared to throw exception. How did I miss that? So this is again, unfortunately, this guy doesn't care about it, but I need that here. But let me go put that in there. So we can see how the, what do we call this? Checked exception is really making this much more complex than it should really be. We don't have to fight that problem, unfortunately, but we're forced to fight the problem here. So where is it complaining? Can anybody see where it's complaining? On line number 11 in account service, of course. Line number 11 is right here. I need to tell him to throw an exception as well. All right. So we can see that the account was done. Let's do one more thing, by the way. Let me go back here and do one small thing. After we deposit the amount, I'm going to output deposited money amount. And then I'm going to say, will it stay? So I'm going to ask, deposited money, will it stay? It says deposited 500, will it stay? Let's see why I'm doing that. I'm going to go back to this code here. And I'm going to ask him to transfer not 500, but 5,000 between these two accounts. I know we're a bit nervous now, isn't it? What's going to happen? Well, let's step into the transfer method first of all. In the transfer method, we get into the transaction, and it says, go ahead and transfer. Give this guy $5,000. And he's like, I'm rich, right? He's happy. And he's running out of the building. Then we go to the withdraw method and say, can I have the 5,000 please? And he's like, what? Are you crazy? I don't have 5,000. I have 1,000 in my account. That transaction is going to blow up. But remember, we are in a nested transaction here. So that's going to blow up the other transaction. The code of silence is broken. At least in theory, what should happen? No money should really be transferred in the hand, isn't it? Let's run this and see if that's true. So run this code. Deposit at 5,000, will it stay? Not enough money from the withdraw. And when we are done, notice we are still left with 1,000 in each, and the money never got transferred. So that tells us that the transaction was running in a cone of silence, except I did something really bad here. I printed that message called deposit 5,000, will it stay? What do you think of that idea? No. In fact, what you run within a transaction must be a pure function. What does it mean, a pure function? It should never have any side effects. Why should it not have any side effects? Anybody? Because of rollback. It may retry several times. And if you had side effects, we're in trouble, isn't it? So things you should never do within a transaction. Print out to the console. Bad idea. Right? Log into the log file. Writing into a files. Writing into a database. Sending email to customers. Right? Bad idea, right? So it's important to not do those things. So don't take this example literally and start writing messages over there. You say, okay, we are able to see the transactional boundary, but we still are not sure, is this really helping? Well, let's do one more thing to just prove this point. I'm going to create two threads, dot start, that's my first thread, and within this thread, I'm going to say new runnable, and to distinguish this, let's go ahead and say in here, I want to transfer $100 between these two accounts. So I'm going to just put 100 as you can see right there. I'm going to start one more thread right here, and in this case I'm going to transfer $200. So you can see there are two different transactions running concurrently, and then of course let's just wait for them to finish. Thread.sleep, let's just give it a little bit time to finish it. Now I want to know if this is really running, so within the method for the transaction I'm going to say transferring, and I'm going to specify the amount I'm transferring. So notice what's going to happen. Two threads are running concurrently, two transactions running concurrently. They both are trying to transfer money, one transferring 100, another transferring 300. We can see how this gets into a contention mode. So when I run this, notice, I haven't written any extra code to handle this, but when I run this little code, notice it says transferring 100, transferring 200, but one of them won. I don't know which one won in this case. Oh, it looks like the 100 really finished. And notice that transferring 200 was automatically restarted. We didn't write any code for the restarting of it, right? Because it went in there to realize, oh wait, this guy has a contention. One guy finished, I'm here sitting with the stale data, and it restarts itself and repeats the transaction. One of them finished, the other one repeated. So what we just saw here is the so-called software transactional memory, and we saw how to use it. So when do we really make use of STM? STM is an interesting solution, and it is very useful when you have frequent reads and frequent writes, but very infrequent write collisions. Meaning, you can have concurrent reads and concurrent writes as long as they don't step on each other. Think about this as, we have three doors in this room. I could be exiting through the right door and you could be exiting through the left door, and we don't have to yield to each other. But if multiple people go towards the same door, like in the case of an elevator, as civilized people, what do? We say, after you please, and then we make another attempt to enter the elevator. It's the same model here. When multiple transactions compete to change exactly the same data, it yields to one and the other retries automatically. What's the catch? The catch is, this requires the transaction to be very pure. And it also requires the state to be immutable. Well, there's a really good news in Clojure, because in the language Clojure, everything is immutable except the managed mutable identity. In Java, everything is mutable except the ones you remember not to make mutable. So we are in a real trouble with Java. That's one of the biggest unfortunate things, is we have to make sure that we don't mess up and start mutating things in between. So I'm going to say that almost every language has this problem, but Clojure makes it a lot easier to work with. In fact, I'm going to say, only in Clojure, it's really safe to do concurrency today. In every language, they give you APIs and a loaded gun with it. So we have to be very careful programming with them. We still have to scrutinize it. But the beauty of this is, at least it's a little bit easier to deal with than forgetting to synchronize and suffering through the consequences of that. So that is the STM model. I'm going to switch gears and show you a different way of doing things here. This is fundamentally a different approach. This is actor-based concurrency, predominantly evolved from Erlang and came into the came into the JVM through the model in Scala itself, and that's kind of taking a little bit more prominence. Go ahead, please.
So, indicate once again what's happening under the hood when you specify this ref class. So the closure, there's an immutable object.
So the question is, what is really happening under the covers when you use the ref class? So what's happening is we created a special kind of an object called a managed immutable identity, which is the ref object. Now, one of the things we have to guarantee is that the ref object always points to an immutable state. In this example, we pointed the ref object, so-called balance, to a big I integer, and we know in Java integers are immutable, we cannot change their values. So imagine I'm the managed mutable identity, and I'm pointing to you, which is the current state of the object, but you are immutable, you cannot be changed at this point. At a later time, I have a new balance. Rather than changing the value, we created a new value, and then we said, flip the switch and point to the new value, letting go of the old value, right? Now, of course, the whole old value could remain for historic reasons, or could be disposed of, we don't care about it. So the point really is that this is a very special object known as the managed mutable identity. Now, the key things here are that you cannot modify the object that it points to, that has to be immutable. You can change the reference to point to a new reference, and you can only change the reference when you are within a transaction. If you try to change it without getting into a transaction, the managed object keeps its eye open and immediately screams saying, you didn't enter a transaction, you have no rights to modify this object at the moment, so protecting us from modifying this incorrectly. And when we do get into a transaction, the rest of it is managed by the STM transactioning to make sure that when there is contention, it resolves by letting one guy win and repeats the other ones so that they can yield and succeed eventually. And there are some more logic, of course, under the covers to make sure there's not much starvation for a long-running transaction, meaning not a long-running basically, but the older transaction, so that it can be prioritized to get this completed as well, so there are a few things to take care of that. So one other approach, by the way, is the so-called actor-based concurrency, like I said, brought to JVM through Scala from Erlang. Now, what does actor-based concurrency really do? I'll give you a quick example here, and depending on the time we have, I may be able to expand into that example. And basically, the idea here is quite the opposite. Well, shared mutability causes problem. We want to completely get rid of that. Well, the extreme case is total immutability, like functional programming says, and of course, we cannot really afford to do that. So what are we going to do here instead? We are saying, I'm going to have what is called an isolated mutability. Isolated mutability is different from encapsulation though. Encapsulation is where I have a data, I have provided you methods that want to access this data. You cannot touch the data directly, but you can ask my method to run. Unfortunately though, when you call multiple threads on this object across these methods, I have to worry about thread safety at this point, right? But the point really in here is, rather than encapsulation, we are isolating the threads. So managed, in this case, the idea is the isolated mutability simply says, when multiple threads ask the object to do some work, the object guarantees that only one thread will run at any given time. That's guaranteed. Let's think about an example for a minute. Well, let me pick on Chuck again as an example here. We got Chuck and he's got a phone number, but he's busy in a meeting. He's not going to answer his phone right now. I'm going to call Chuck and you're going to call Chuck exactly at the same time. Who's going to be able to leave a message because he's not picking up the phone? Both of us, right? Absolutely. Multiple of us can call at the same time and leave messages for him. So this is purely asynchronous, also known as a fire and forget model. We can simply send message to him and move on. Well, Chuck comes back from his meeting, looks at his phone and says, boy, it's been a busy day. Look at all the messages that are waiting for me. He's going to start listening to these messages. How many messages can Chuck listen to at any given time? 12. This man is evil. Okay, he doesn't understand them. That's the suffered model again, right? So if you were to understand the messages, how many do you listen to at any given time? One at a time. Even though he has 2 ears, he listens to only one message at a time. Why? Because he tried multiple messages and he realized that multitasking sucks, right? And over the time he realized that he can take one message at a time, either finish it or delegate it, and then move on to the next message. That's exactly the case about actors. So actors are little objects that run in their own thread, and we can send messages to actors. Rather than calling methods, we send messages. And the actors themselves happily sit there and receive these messages and process them over and over as the messages arrive, but only one message will be processed at any given time, not multiple messages at the same time. So let's take a look at an example of how that could be used in an example here. I'm going to create a simple actor here for us to understand, and then we'll go into a little bit more complexity if time were to permit. So let's take a look at an example of what I want to do. We've got to create an actor first of all. What kind of actor can I create? Well, we need an application to use actors, a library or a framework or a tool. I used STM earlier, and I used Clojure STM. By the way, there are multiple different implementations of STM also available on the JVM. One of them is called Multiverse, for example, which is an API available. Scala has STM implementation as well. So there are multiple different implementations of STM. When it comes to actors, there are about 7 to 10 libraries available. I mean, you know this already. That's the beauty of the Java world, right? We can never have one solution that works. We can always have 10 to fight against each other, and we can spend the time figuring out. Same thing with actors as well. There are multiple different actor libraries available for us to pick and choose. I'm going to use just one of them, which is pretty good here, which is called the Akka library. And Akka basically is written in Scala, but we're going to use it from Java here because it's just a library. Just like we reach into Spring or Hibernate, we're going to just reach into it and use it here. Let's see how we're going to use that here. So what I'm going to do first of all here is I'm going to import akka.actor.star to bring in the imported package. And I'm going to say actor system. I need access to the system itself. I'm going to say actor system. And this is going to be actor system.create. And one of the first things I remember to do is I simply say actor system.shutdown because we don't need it anymore at the very end of this. But we've got to create an actor and use it. What kind of actor can I create? So actor ref, I'm going to create an actor. Well, we don't have to look far enough, right? We can create a Hollywood actor, isn't it? So we can simply say Depp. Depp is a favorite actor because my children keep seeing his movies all the time. So I have to say here, actor system dot, and I'm going to say actor of new props. So I'm going to specify the object I want to use here, and this is going to be the Hollywood actor. So Hollywood actor, actor.class. So notice, rather than using new to create this object, we simply used a factory to create it. And the reason is, you want the actor to be created within the library's managed code, so we can have the thread being managed by it automatically, isn't it? So now that I've created the actor, I'm going to say dep.tell, we're sending a message to him, and ask him to act the role of Sparrow for a minute. So that's all my code. Of course, I need to have the actor built up for me to run this part of the code before we go any further. Let's pull up the Hollywood actor here real quick. So you can see that the class Hollywood actor is sitting right here. And I'm going to extend this from untyped actor, which is a base class. And I'm going to provide here a method called onReceive, which is going to take a message. So I'm going to say final object message as a parameter to send to him. So essentially, on the client side, we call the tell method. On the server side, we are calling an onReceive method to say, run this when a method is a message arrives. So we don't have to deal with messaging ourselves. The library takes care of that for us. So when a message arrives, it says ding, and there's a message popping up, and Chuck can be actively working on it, but until that, he can just relax and view his iPod and have a good time, right? So the point really is that it is sent to him, and he can receive and process that. So how do I really work with this here? So I'm going to say playing, and I'm going to simply display the message we are playing here. So I'm going to print this message, that's all I'm going to do, on this side, and notice in this side, I'm just telling him what to do and run the code. You can see that it says playing Sparrow, and it tells us it's played that message. But of course we are curious, what really happened over here? To make this a little bit more interesting, let's go ahead and say in main, and I'm going to specify the thread.current thread, so we can see where the thread is in the main itself. And of course, that should be no surprise. Main is running in the main thread. But I'm also going to go back to this code, the actor itself, and then say plus, and after the message itself, I will say in, and let's go ahead and display the thread information for us to see in the actor itself. This time, notice that in this particular case, I'm going to specify the thread he is running in. So let's fix this first of all. So this is going to be thread.current thread. That's what I want to fix over here. So what did I do? Anybody sees that wrong? Oh, plus 2 pluses. Thank you. So right there is the plus message. Thank you. So you can see that in this case, look at that. The main is running in the main thread, but on the other hand, Sparrow is running in a totally different thread. And what thread is he running in? He turns out he's running in a dispatcher thread of some kind. In fact, if I lower the font here a little bit, we can probably see the dispatcher thread number. Hey, that's a 1, as you can see here. Did you notice we never create a thread in our code, but automatically it runs in a separate thread? And the reason is actors run in their own threads. What if I have multiple actors at the same time? Well, let's go back and try that one more time. So this time I'm going to create yet another actor, and this actor I'm going to call as Hanks over here, and I'm going to say Hanks to do some work here. So Hanks.tell, and in this case I'm going to say here, let's say Gump. So we're going to ask him to play another, this actor to play a different role, but you can see that they both are running concurrent. Let me raise this up here for you. You can see they both are running concurrently, but you can see that Sparrow is running in thread 1 and Hanks is concurrently running in thread 2. So every actor runs in its own separate thread at any given time, so they can be concurrent. But what about one actor? What if multiple messages are sent to one actor at the same time? So going back over here, notice right after I send the Sparrow message, I'm going to say requested Sparrow, and I'm going to also say output here requested, let's say requested Gump. So then I'm going to go back and do 2 more messages, if you will. This time I'm going to tell Depp to play, let's say, Wonka, and I'm going to ask him to play Lovell here. And of course, in this case, we can see what happens. So I'm sending these 4 messages, 1 message at a time, but notice that the main is not going to wait for that. The main simply runs through, and it's an asynchronous request. So you can see all the request messages are piled up in the top, and they are queued up in the object to be processed. And notice though, that Sparrow is on thread 3 and Wonka is on thread 3 as well. That tells us that it was processed sequentially, one after the other. And multiple actors can run at the same time, but any given actor only does one work at any given time and then moves on to the next one. Of course, looking at this, we may say, gosh, if that is true, is it true that actors hold these threads hostage? Fortunately, no. The library maintains a pool of threads and lets the pool of threads shared by the actors. When an actor doesn't have any message to process, it doesn't hold on to these threads. Think of a thread to an actor as a waiter to a restaurant table. The waiter doesn't wait on the table, but switches between multiple tables as the need may be. In a similar way, the thread from the thread pool shuffles between the actors and provides their needs as and when messages are available for them to process. But the guarantee here is no 2 threads will enter that particular actor at any given time, any given instance. Only 1 at most will be in an actor at any given time. So this gives a fairly decent amount of scalability in the code as well, as we can see. So given this, how do we really put something useful with this? Let's take a look at an example of how we could apply this. So let me say that I have a stock info class right here. The stock info is a fairly simple POJO object. All that the stock info says is, I will print out the stock information, the price and the ticker information. That's all it does. Great. Now I'm going to create an actor. I call it a stock collector. Now I want you to focus on this part for a minute. Now all this you see here in this part is, I would like to call these as not encapsulated variables, but as the isolated mutable variables. Because these are part of an actor, no two threads will modify these mutable variables at the same time. They are mutable, but they are isolated. And in the onReceive method, I'm simply using the logic. So as the message arrives, meaning the stock information arrives, I compute the maximum, whichever stock is maximum, and I'm going to reset the stock high price. No need to read the code inside the onReceive, because that's purely logic that we are used to writing, isn't it? But the point really is that the onReceive is going to be called, and I'm going to send him a stock info object, and based on what I send him, he will compare and update the highest price value for us. How am I going to use all of this stuff? So here's an example of using all of this stuff. Let's first of all go ahead and write this sequentially and play with this first of all. So I'm going to go to Yahoo and get the stock prices. So I'm going to say over here, first of all, this is a sequential code I'm going to write. I measure the current time. I ask him to create an empty stock price. Here is a traditional for loop. And within the for loop, I'm simply looping through and getting the Yahoo Finance get price. You can take a look at this code on my website and see what this parsing code does. It's really not a culture to show parsing code in public these days. So I won't show the parsing code, but you can take a look at it in the privacy of your home or office, right? And all that it's doing is getting the price for us and giving us, and then I'm comparing the price and saying, all right, here's the highest price based on what we were given. So I want to go ahead and call this do sequential function, and this is going to go to Yahoo and get the highest stock price based on whatever we have right now. Of course, that requires internet connection, which I don't seem to have at the moment. Let's see if I'm able to connect to it. So essentially that's what I'm doing is simply going out to Yahoo and getting the price. Now how do I do this concurrently if I wanted to do this concurrently? Let's talk about concurrent application of this. Now that shouldn't be too hard to do. So do concurrent. What I'm going to do here is simply start out by creating an actor system, as you can see right here. And once I get the actor system, I'm going to say create me a stock collector. And once you create a stock collector, tell him how many stock prices I'm going to expect. And then I go through a loop, as you would imagine. But within the loop, I'm simply delegating this to a thread and saying, hey, you thread, go get the stock price from Yahoo. And when you come back, please go ahead and tell the collector that's the price you have so far. Notice we don't have any locks over here as well. And of course, I'm not able to connect to the internet, so I won't be able to show it to you here. But this code is on my website, you can try it. But you will notice that in this particular case, it would take anywhere from 20 to 30 to 40 seconds on the sequential, but the concurrent would take less than a second or about 2 seconds to run because it runs concurrently. But essentially what I've shown you here is something very simple. We definitely want to avoid synchronization as much as possible because synchronization is extremely hard for us to reason. And anytime we have to lock something, we have to sit there and stare at it and say, is this locking properly? Am I doing the right thing? It's extremely hard to reason that code and errors creep in. So by looking at these two models, what we have decided to do here is completely avoid synchronization. And then we said, let's focus on creating a simple model that's easy to understand, easy to reason, easy to prove that this is doing what it's supposed to do. Now that we don't have to deal with locks, we got several things really removed from our shoulders, right? You feel a little lighter today, right? Why? When you don't have to lock, you don't have to worry about where to lock, when to lock, which objects to lock, which level to lock. Did we lock at the right time? Did we lock for the right duration? We don't have to do any of those. And that saves us so much effort and time. And we can develop code focusing on the problem we are trying to solve rather than chasing behind synchronization problems. So these libraries are available on the JVM. That's what the beauty of that is. So we can program them in any language, but of course there are a few things we have to be careful about. And when it comes to Actor itself, Actor is useful when you want to have a separate task running for a long time. Think about like a printer in your department, right? You can send multiple jobs to the printer, you can send jobs to multiple printers, but you'll be very upset if a printer interleaves papers, like some printers sometimes do, right? So that's where the concurrency issue is taken care, and coarse-grained things can be passed around pretty easily. If you're interested further, you can download this code right from that URL, and I posted that right before this talk, and you should be able to get to that. Thank you very much for your time. Good question.